Got it. So, okay, of course, I mean, today I would like it to be a little bit more interactive if possible than last time. So if you have any question or something it's not clear, I mean, without any problem, you can interrupt me and we can take our time to go through all the questions. So the tutorial was structured mainly in two different exercises. The first was about using OPES for sampling expanded ensembles, or the kind of ensembles that you can sample with replica exchange, for instance, and this kind of methods. And the second exercise was about using OPES for metadynamics-like simulation. So to sample basically a collective variable, and hence the sampling along a chosen collective variable. I thought that we could start from the second exercise. That's probably, I guess, the one that it's most interesting for the majority of you. And so, yeah, but of course, again, if you have any questions, you can just interrupt me. So basically, in this tutorial, we were simulating the molecule of alanine dipeptide, which is the same that was used also in other master classes. So I didn't introduce the molecule. What's important to know is that this molecule has two main stable states that can be distinguished using this phi angle. And so if you can plot the free energy along this phi angle, there is a barrier and the two main bases. You can also plot the two dimension using another collective variable, which is the psi angle, and it would look like this. So again, one basin with two minima that are connected, and a second basin. So this is our system. It's a toy model, but I think it's very useful to test and sampling methods. Here I put a bunch of details about the system. I have a converged free energy on 1 dimension and 2 dimension, and the free energy difference between the two basins that I obtained simply by a very long OPES simulation. We are going to look at these three methods. Well, regular well-tempered metadynamics, the OPES method, and the Explorer variant of the OPES method. We start simply by biasing the phi collective variable, and here it was a very simple. I mean, I gave you all the inputs, and you can see basically that by biasing on this phi angle, you can go back and forth from the two main basins. And here I was plotting the bias just to show how in metadynamics, the bias keeps on growing. Whereas in OPES, there is a different way. The bias converges to a fixed value. So you can see here it does not grow over time. The idea of this first exercise was just to get used to what's the output of an OPES simulation, and I think comparing it to metadynamics, if you are used to that method, it can be helpful. There are a bunch of quantities that one can plot in order to have a quick understanding of how your OPES simulation is going. One is this RCT, which is also present in metadynamics. It's defined in this way. And then basically, in metadynamics, it keeps track of how much the bias grows. And in OPES, since the bias is not growing, this simply converges to a constant. So if you plot this, you have a very quick, even if you're biasing 6 or 7 collective variable, you can just plot this and have a quick idea if you are converging or not. Similarly, this Z variable should converge to a constant, and it's a way to have an idea if you're exploring new regions of the collective variable space or not. And the other part that I think it's interesting to look at in an OPES simulation is the number of compressed kernels that we are using, which also should slowly plateau, and the effective sample size of the simulation. And this instead should keep on growing. The effective sample size is basically, I don't remember if yeah, I think I said something about it before. It's a very standard way to quantify. So since we are doing important sampling, so we are not directly sampling the Boltzmann distribution, but a biased version of it. The sampling size would be just the number of samples that we have, but we can define this quantity, the effective sample size, which tells you out of here it's 1,000 points. We effectively sampled our simulation is equivalent to sampling the unbiased distribution for just 400 points. And this is normal because when you do reweighting, you are exploring regions that have very low probability, and this is something that you want because you want to be able to explore, for instance, the transition state. But this means that their weight is very low. So actually, you shouldn't be sampling them. No, those won't count as a full sample when you do the reweighting. So effectively, these very high free energy regions are useful to explore and to sample. But if you need to collect statistics about an observable, those are useless because the actual weight that they give to, for instance, an ensemble average is basically 0. So this effective sample size is a very simple proxy to tell you how efficient is your sampling. I mean, this is very important, especially for when you sample expanded ensembles. So I will talk a little bit more about that, but it's just something that should always grow. And here you can see the comparison, the number of points. So every time you sample a new point, you are supposed to add a kernel, but then you compress them. And as you can see, the compression is very efficient in reducing the cost of evaluating the bias. And the effective sample size, roughly 1/2, it's a reasonable value for when you're sampling the well-tempered ensemble. And you can also look at the kernel bandwidth that is supposed to shrink over time. Then what you can do is you can look at the free energy surface. There are two ways to do this. One is to just look at the bias. You know the relationship between the free energy and the bias, and this is the same as in metadynamics. If you're familiar with metadynamics, again, the sum-ILS does this. You calculate actually the bias that you are using, and you use this as an estimate for your free energy. And this small script does that. And I should run this. So we are now in this folder. And what you see, this is the difference in free energy estimate as obtained directly from the bias. So this gives you an idea of what kind of bias we are applying for OPES and for metadynamics. As you can see, they're both very good, and they have small oscillations around the true value. Here we just plot the free energy difference between the two bases. And just a curious thing, here we set a value for the barrier keyword, which, if I remember correctly, okay, so here the value for the barrier was 40. And we can see this is enough to cross the main barrier between the two basins. And we just sample a little bit above 40, but we don't sample this very high free energy region. And this can be very useful because sometimes, okay, in this case, the variable is periodic, so you cannot push the system into weird states by pushing on this variable. But sometimes you really don't want to go to explore too much. You are interested into going into, at the end of the day, into calculating this free energy difference. And once you cross this barrier, that's fine for you. So with OPES, you can decide not to sample this region, and this is shown by this. So the estimate of your free energy, of course, won't be reliable above 40. Whereas metadynamics starts slowly and keeps on increasing, and eventually it will sample any value of the free energy if you wait long enough. Instead, OPES, it's quicker. If you look at the beginning of the movie, it's quicker in sampling this barrier and making the transition. You see, it already has an estimate very close to the final one, and also oscillates less. This is the typical. This is a typical example of what it's doing. So it's faster, since you are providing the expected barrier. OPES is faster in crossing this kind of barriers and will never go much above. Instead, metadynamics starts slowly and keeps on filling. This is one of the main differences from a practical point of view. Okay, the other way to estimate the free energy is through reweighting. Reweighting it's very easy. You can do it with the Plume driver. And again, in the previous master classes, I think it was in the one about 21.4, the one about metadynamics, they explain how to do reweighting with the Plume driver. Here I prefer to use Python. And there are libraries that do kernel density estimation. You can use those. Usually they don't handle periodic CVs. So here I just rewrote an equivalent script for that. And you can find it on the GitHub repository. The result of this reweighting, as you can see here, we don't have samples because we said we don't want to cross this kind of barriers. And in fact, the reweighting is completely is completely wrong. For metadynamics, there are a lot of ways to do reweighting for metadynamics. Here, I've chosen probably the two most used, which is one based on this C of T, and the other one based on the last bias. So you take the last estimate of your bias and you use it as a static bias to do reweighting. In this example, where the collective variable is very good, you have a ton of transitions in between the two states. Everything is completely at convergence. Basically, anything that you do will work. So both these ways of reweighting metadynamics are pretty accurate, and also the sum is pretty accurate. It oscillates a little bit. Usually what people do, take a time average. They arbitrarily choose from where to start. Then you take a time average to have a good estimate of the. And of course, you should do block averaging to get an error also on your estimate and so on. Any question about this this first part? Maybe I can simply say one thing about the input of the OPES simulation. Again, you have to choose the barrier. Here we explicitly set a value for the sigma. If you don't do this, you will try to guess a correct value on its own. And these three lines are basically dumping the state of the simulation to a file. The state of the simulation is basically a list with all the compressed kernels that OPES uses. We need this in order to calculate this estimate from the bias. But if you just want to do reweighting, you can skip these three lines. They're not needed. And of course, if you forgot to add them during the simulation, you can also use do a rerun and just calculate the state file without rerunning the actual simulation. So this is just to have more output from the OPES simulation. I don't know, are you familiar with Plumed? Have you used it before? Because otherwise what I'm saying it would be rather okay.
Yeah, a quick question, if I may.
Yes, sure.
There's some small paragraph about the number of the condensed kernels, and for long simulation needing to use like fixed sigma or something like that. I didn't quite understood what was the issue there.
So yes, basically, as you can see, the number of kernels keeps on growing. So it's never constant. And the reason is that we start with a broad, we wanted this behavior to happen, no? So we wanted to, as soon as possible, cross the barrier that we chose and start sampling the two states. And what we really care about are not the details of the free energy surface, but is the difference in free energy. So, because this is the rare event, no? The shape of the basin, it's easy to get. What's hard, it's the free energy difference between the two. So what OPES does, it starts with very broad kernels. So the first, maybe I can stop this. For instance, at 0. Let's see if it works. No, 1. So, okay, here we placed, I think, something like 10 kernels or maybe less. And what you have, you see, it's metadynamics has placed a bunch of Gaussians in the minimum. Here we placed a very broad kernel. Here you see this is one single kernel, and it already has the full shape of the minimum. So you start with very broad kernels with a broad bandwidth, and then the bandwidth shrinks so that you are able to get the actual shape of the free energy. The problem is the bandwidth will always shrink, so it keeps on shrinking, and the shrinking is proportional to the effective sample size. These are standard thing for kernel density estimation. I didn't know them, but if you go in the literature, these are standard things. So if the bandwidth keeps on shrinking, then the number of kernels that you place will increase, because the average distance between two kernels is 1 sigma. But if the sigma shrinks, then you will increase the number of kernels. This is not a problem usually, because you see, after 400 you are about 30, and then at 1,000 you are still below 40, no? So it's growing very slowly. So usually it's not a problem. But let's say that you need your simulation to be 100 times longer than this, no? This will keep on growing. And especially in higher dimensions, where the number of kernels, it's not 40, but maybe it's already 1,000. Maybe you don't care about going so to this level of detail, no, of the free energy. You can always do that during reweighting. So you can just, from a practical point of view, if you restart your simulation, you can add this fixed sigma keyword, and then the sigma is going to stay fixed, which means that also the number of kernels will not increase. So it's or if you know beforehand a reasonable value for the minimum size of the bandwidth, then you can set it and you won't go below that. I usually don't do this, but if you, for an application, you might need to run a very long simulation, and then this can be useful.
So is there like a performance cost for like ever increasing the number of kernels, or?
Yes, basically the bias, I have the formula somewhere. So the bias is built as the sum of all the kernels. Because you need the sum of all the kernels to get the estimate of the probability, and that goes into the bias. So the more kernels you have, the slower this sum is. There is one thing that you can do to speed this up without stopping, without removing the. Of course, you can do many things if this is your issue. You can increase the threshold for the kernel compression algorithm. Then instead of when the kernels are closer than 2 sigma instead of just 1 sigma, you will merge them. So you will roughly have half of the kernels, but you will have also a rougher estimate of your free energy. Or you can use a neighbor list. So there is this keyword, and we will see it in the following example in 2 dimensions. I always use it in 2 dimensions. And the neighbor list, of course, in order to know the value of the bias here, you don't need to sum also kernels that are here, so far away. So you need only, since the kernels are Gaussians, they decrease quite fast. So you only need the kernels that are within a reasonable radius of where you are. So you can define a neighbor list, and this speeds things up a lot, especially in higher dimensions. So yeah, there are a bunch of tools that one can use to, if performance is a bottleneck. I would start with the default. Of course, neighbor list in more than 1 dimension, I would strongly suggest it. But before setting a minimum value of sigma and so on, I mean, also everything is parallelized. So if you are running on OpenMP or MPI, also this sum is parallelized, and often the bottleneck is somewhere else, of performance, and not here.
Thank you very much.
So the next straightforward step is to bias instead of 1, 2 collective variables. And the nice thing, I believe, of OPES is that if you look at the input file, it's again basically identical. This is the keyword for the neighbor list. We can add that, but conceptually, the 2 things are equivalent. So that's I think it's very handy. In the let's start with this. I gave you a very short simulation, and we can see, okay, this is the reference free energy that we should get at the end of our simulation. Again, what I did was to run both an OPES and an OPES Explorer simulation for Alanine. And here we can see this kernel merging in action, and the fact that I was explaining before. So at the beginning, you place very big kernels, and you have a very coarse estimate, and then you make a transition. This is a very short simulation. So we are visualizing each new kernel added, and you can see sometimes you add a new kernel, sometimes you merge the 2, and the kernel just move a little bit. So in just 100 picoseconds, we place 100 kernels, and in OPES we have 1 transition. In metadynamics we have 0. I don't know if you tried to run it, you will see it. So in this short amount of time, you don't make a transition. And in OPES Explorer, instead, as you can see, you place fewer kernels, much broader, and this also gives you a faster exploration of the space. And you are making in this very short amount of time, you make a bunch of transitions. And you can also, as before, plot the free energy difference estimate. Again, it's just 100 picoseconds, and both estimates are very bad. What I did was just to run a longer simulation. And And then you can see the free energy will start to look more like the target one that I showed you above. This is nice in 2-dimensional. We can visualize it. What I usually do when I'm working with more than 2 collective variables is not to plot this free energy surface, but just maybe to look only at the free energy difference. And you can see this OPES Explorer is going much faster, and the estimate oscillates more, as we said before. If we run metadynamics, the picture is very similar to this one. So more oscillation, and but in the end, the estimate is very similar. And this is the free energy estimate. Of course, this is just from one simulation. If you run your, maybe it looks different from mine. But on average, since these 2 collective variables are very good, they should, on this time scale, they should look quite similar. We can also do, again, the estimate from reweighting. Here I give you a script in Python to do that has the same syntax of the Plume sum hills. And if you do that here, I think I added also the metadynamics run. Oh no, I didn't. Anyway, you can do the reweighting, and for OPES, it looks extremely similar to the direct estimate. So as a matter of fact, you can skip printing down the state of the OPES simulation and just look at the reweighting. That's perfectly fine. And you can see that for OPES Explorer, the oscillations are basically gone from the reweighting estimate. And I think, okay, I also said metadynamics, if you can run the reweighting from metadynamics, and it will look very similar also to those of OPES and OPES. I mean, this was a very straightforward example. The main reason was just to show you how to make post-processing of the OPES simulation. If you go to more than 2 dimensions, 2 collective variable, here I was using Alanine tetrapeptide, which has 3 phi angles. And I just ran a simulation with, again, OPES Explorer, and metadynamics. What I'm plotting here, okay, now we are looking at a 6-dimensional collective variable space. So of course, it's harder to say where you are. In the example of in 1 dimension, we could just plot 1 collective variable, and we know if we are down here, we are in 1 basin. If we are up there, we are in another. In this case, I had a small script that checks on the value of all of the 3 collective variables and tells you in which state you are and what's the total number of states that you have visited. And you can see the difference. OPES Explorer gets to see all the 8 metastable states much faster. And for metadynamics, depends on what input you choose. So in this example, what I wanted to do was to use some default values. So again, this is the input for the alanine tetrapeptide, and the OPES input is identical. And least, now it's very important. If you don't put it, the simulation will be much slower. And I just add 3 collective variables. For metadynamics, I did the same. So this is a typical input for alanine dipeptide. The value of sigma 0.2, sometimes it's 0.3, 0.35. The height is 1.2, and the bias factor. So I use the same input for alanine tetrapeptide. Of course, this was Of course, now you have to define a three-dimensional grid and so on, and what you get is a very slow exploration. So in 1,000 picoseconds, you just visit for. If you change, for instance, you put the height equal to 12 instead of to 1.2, which is really a lot, you will have faster exploration, but then the convergence will be worse. So there's a trade-off. You have to take care of all of this. The main point of this was to show how it's easy to scale up the number of dimensions by using OPES. From such a short simulation, I don't expect to give a reasonable estimate of the free energy. So this was mainly just to show I have space that I need to sample, and as I said in the presentation, sometimes this is something. I mean, the main thing that you care about, seeing which are the metastable states, and being able to do it quickly, it can be useful. I don't know if you have questions about this part. I think I asked you to try to play around, like, for instance, to change the bias factor and see what's the effect on the sampling efficiency, or to remove the Z term, which is this normalization over the explored space. Well, if you do that, you will see that the exploration will be much slower. So, I mean, it's just to have a sense of how the method works and what the pieces of the method do. Okay, I don't know if something was not clear, or did you manage to run this system, also the bigger one? Also, I didn't know. I tried to have simulations that would run quite fast in. Okay, then okay, this I think is maybe the more interesting example, biasing a suboptimal collective variable. So in reality, in any practical application, you are never in the situation of having of alanine dipeptide with the phi angle. So usually your collective variable describe a slow mode of the system, but not all the slow modes of the system. So there might be still, you might still need to wait a long time in order to see a transition. And you can see these in, for instance, in the paper that introduces OPES Explorer, we used as an example this Muller potential, where if we bias only along the X, we can see the two minima, but the biased free energy, which is this one. So this is the free energy, the potential energy, because it's just two-dimensional, plus the bias along the X, the optimal bias. You can see still there is a bottleneck in between the two states, because we are not biasing on the other slow degree of freedom, which is Y. So this is a very simple and clear to see example, because it's just two-dimensional. If you want to run this, you can find all the inputs on the PLUMED nest. Here I wanted to stick with alanine dipeptide, and so I went to the masterclass about metadynamics, and in the solutions, they proposed this is the notebook of masterclass 21.4 about the one about metadynamics, and they asked as an exercise to try to find new collective variables for alanine dipeptide. And in the solutions, you can find this collective variable, which is basically built as a complicated expression, but is built starting from the RMSD, from basin A and basin B. So you take one configuration from basin A, one configuration from basin B, and you calculate a distance from this reference configuration. and you build this collective variable as a path collective variable. So basically, in this collective variable is telling you how far you are from these two references. And it's a collective variable that goes from 1 to 2, more or less, I think. And of course, if you are in 1, you are closer to Bayesian 1. If you are in 2, you're closer to Bayesian 2. And this is brought as an example of a bad collective variable, because you can see you have fewer transitions in between the two states. So now, again, it becomes important, this idea of how do you choose the proper parameters. I don't know if you've tried to run this and to choose parameters for metadynamics. So, so again, here the RMSD distance from Bayesian A and from Bayesian B, and our collective variable S. So in metadynamics here, the problem is that you're using a collective variable that you don't know. So choosing the sigma might not be trivial. You have to run some simulation and see. And the grid that goes from 0 to 3, again, it's nothing hard to do, but you have to run a bunch of preliminary simulations, and then you know what's the range of your collective variable. Or the idea is that in this case, you could also analytically know, since you write down the expression, you could analytically know what's the range of this collective variable and so on. But let's say that you are using a collective variable that comes from a machine learning procedure, no? Then you don't have a physical intuition of what's going on. So choosing the bias factor, choosing the height of the might not be trivial. I don't know if you picked exactly these values. I just copied them from the solutions of the previous masterclass, and with these inputs, I can run simulations with metadynamics. Before, I never did block analysis or anything. Here, I gave you the input to run at least 4 independent simulations, so you can get a sense of what's going on, and you can get a very rough estimate of what's the uncertainty of your estimate. And for OPES, instead, the first guess that one can try is just, again, to do the same. So you don't expect, I mean, the barrier, the free energy barrier, actually, since I told you that this is a suboptimal collective variable, you expect the barrier to be smaller. Why? Because the collective variable, the free energy along this collective variable, will have a smaller barrier in between the two, because let's say, how to say this, this is the slow mode that is describing as only this barrier in between the two states. So the perfect collective variable will have the highest barrier in between the two basins. So to cross this barrier, it will take the longer time, no? If I choose a collective variable, for instance, that's super bad, that does not even distinguishes between the two basins, then the barrier between the two basins is 0, no? And if I add a bias potential along this very bad collective variable, I basically am not crossing any barrier, no? So this is something that is always true. The better the collective variable, the higher the barrier. Of course, until you have the optimal collective variable, and that's the real barrier in between the two metastable states. But if your collective variable is less than optimal, then you should expect a smaller barrier. I don't know if this it's clear, if I was able to explain it properly. But yeah, the idea is the better the collective variable, the higher you will with the barrier. So one could say, okay, most probably 40 was already more than what we needed for the phi. So we could guess that the barrier here that we should put is smaller, but we can also leave 40 and see what happens. If I run this with OPES, again, here as before, I'm plotting the free energy along this collective variable for these 4 different completely independent replicas. And, and what we see is that we get something kind of reasonable, and I can plot the free energy difference. So in this case, this would be basin A. This is the highest barrier. As we see, it's around 30 or 25, so smaller. And the final estimate, it's not perfect because, again, we are just running 100 picoseconds, and this collective variable is worse than the previous one. So, I mean, it's reasonable to not have a perfect estimate. And here I'm just plotting all the different estimates for the free energy difference. What's interesting is that the free energy difference between the 2 basins is not a function of, it does not depend on the specific collective variable. So the height of the barrier depends on the collective variable. And if I have a suboptimal collective variable, I will see a smaller barrier, because along this degree of freedom, I have a smaller barrier to cross, because part of the barrier is not captured by this collective variable. No? Whereas the free energy difference is just provided that you are able to distinguish between the 2 states, it's the same. So it's the free energy difference between the basin is much less sensitive to the choice of the collective variable. And what we have here is an estimate that is out of this just for simulation, it's compatible with the true value. So I mean, I think it's not a bad result. If we run metadynamics, you can see also from the movie, there is again a much broad oscillation of the estimates. And if I don't know what parameters you picked, but if you choose a different bias factor or a different initial height, this will change. So you can have even more oscillations or maybe less. But the typical trend is the same. And this is the free energy estimate, free energy difference between the 2 basins. As you can see, the single estimate, which is dashed below, it's oscillating a lot more than what we had for OPES. And the average in green with the standard deviation highlighted is also oscillating. So these were completely independent replicas taken from different initial conditions, but still you have a kind of a correlation in between them. And that's because you are putting so much bias, and that it takes time to see the real potential underneath. No, so if you put too much bias, you will cross from one basin to the other, but through a very high free energy region. I can show you this in the simpler example of the Muller potential. So if I'm here and I'm adding a lot of bias along the X collective variable, so I'm pushing a lot along X, it's easier that I cross through this region than that I cross through this one. Because in order to cross here, I need to wait for an oscillation along Y, whereas I'm pushing along X. So this is to give you an idea why with a suboptimal collective variable, if your bias it's changing very quickly, you can cross not through the real transition state, but through some other higher free energy pathway, and the result is this one. So your estimate of the free energy will keep on changing because you are overshooting, you're putting too much bias, and then you have to compensate in order to be able to go back. And this is this oscillatory thing. So what you get in the end is something like this. Of course, if you wait long enough, metadynamics will converge, and all of the 4 replicas will give you the same estimate, ideally, and you will have a flat something much better. But the whole point of this is oftentimes, basically all the time that you use an ensampling, you are actually in this situation. So your collective variable is not perfect. Your system is probably expensive, so you cannot wait for this to be extremely converged. And you have to stop earlier. If you do that, the whole point of the OPES method was to improve on this aspect of metadynamics. So, of course, if I already know in advance exactly all the details, I can cherry pick the input of metadynamics in order to have the best efficiency, no? But you don't know. I mean, the idea was, can I have a method that without knowing much about my system and my collective variable, can still give me a reliable and efficient estimate? And this was the idea. So if we look at the number of recrossing that we have, so the number of transitions, with metadynamics, we have more transitions in between these 2 states. But the estimate that we can get of the free energy and the free energy difference it's much worse. So the idea is that it's better to have fewer transitions, but a more reliable estimate of your free energy. This is the idea behind OPES. The Explore algorithm, which again was developed because these are there are 2 things that you might be interested in. No? Sometimes you are interested in the free energy difference or the free energy surface. Sometimes you have a very complicated system. You have no hope to converge the free energy. You just want to check what are the metastable states, and then maybe to use this information to then improve on your collective variable. No? And if we run the OPES Explorer in this case, we see the behavior is similar to metadynamics, maybe even worse in a sense of about oscillating. And then you get again a free energy difference estimate. We see a lot of oscillations, and it's slightly better than metadynamics, but really this you will see is slightly different. Probably if you run this on your computer, you will also get a slightly different result than the one I have here. And you can, of course, also run the meta that we already had it. So you can also run the reweighting and see how it goes. The bonus exercise here was just use OPES for a simulation where you used metadynamics before. I don't know if some of you tried this. If you did, I would be curious to know about the results. If you got something better or something worse out of it. You can also write me afterwards. Of course, you don't have to. So, any questions? Any something that you saw that was unexpected by running these examples? Otherwise, I'll move to. Okay. So the other thing you can do with OPES is to sample these expanded ensembles. I again, here I start with probably the easiest of the ensemble, expanded ensembles, which is temperature expanded. So what my goal here is to sample a range of temperatures from 300 to 1000 using OPES. I can show you the input for that. So I will need the energy of the system to do that and define this multi-thermal collective variable. And basically, I just need to tell him that the maximum temperature is 1000 because there are some defaults. So by default, he knows what temperature is running, and by default, he uses that as a minimum temperature. If you only provide the maximum, if you only provide the minimum, he uses that as a maximum temperature. And the other important parameter is how many steps in temperature you have to do. If you run this with replica exchange or parallel tempering, you have to explicitly choose at what temperature your replicas will run. So the number of temperatures and the number of steps. Here, if you leave it alone, you will try to guess the correct number by running a short unbiased. I think here is just 100 steps. He runs as an unbiased simulation, and then he looks at the fluctuations and estimate that. But of course, you can also, if you look at this is the help, or if you look at the manual of PLUMED, you can also set manually all the temperatures as you would in a parallel tempering run. So you can say all of the intermediate temperatures explicitly. And then you call this bias, which is OPES expanded, and you tell to use this expansion collective variable. And the pace is how often you want to update your bias. And this produces, well, the Culver file and this delta F file, which contains the estimate of the free energy difference between the various temperatures. So here the temperatures are, the low one is 300, the highest one is 1000, and it picked this temperature in between. And these are the values of the free energy difference. Let me show you not the numbers, but the plot, which should be clearer. So here is, we can see the, let me run, no, wait. Here we can see that you have transitions along this low degree of freedom phi. This is the bias as a function of the energy. And I colored it with the time, so you can see at the beginning for small times, the bias is wrong, and then it optimizes to the correct value, and all of the points basically lie on the same line. So this is the shape of the bias. It's no longer, as before, the shape of the free energy along with the collective variable. It's a different shape. You can plot the delta Fs, the one of the file I showed you before. Of course, it's a free energy difference between the temperature at which you are running the system and the other temperature that you chose. So the delta F with 300 is always 0 because you are running at 300. And the other two have an initial, again, adjustment, and then they're pretty constant. And again, you can plot this C of t, which is just a quick way to, this should converge to a constant, and it's a way to look and to have an idea of what you're running. Here, I think I did the same simulation, but running 3 multiple walkers. So the idea is that you can run any number of parallel simulations that share the same bias. And this will give you 3 times the amount of sampling in this example. So The nice thing compared to replica exchange is that you can choose any number. So in replica exchange, typically you need a replica for each of the temperatures that you choose. Here you are completely free to choose. And so the dashed lines are the one from the single run, the single walker. And you can see they converge to the same values as they should. And the C of t has smaller oscillations at the beginning. So it's converging faster because, again, we are running 3 parallel simulations, so we have better sampling. Here I go into the details how this free energy difference are calculated. This is just a reweighting formula, the usual one. I can plot so I can reweight at any temperature between 300 and 1000. And this is just a way to visualize the value of the reweight. So again, the probability at 300 of being on the transition state is almost 0. But I do sample points here because instead at 1000 Kelvin, the probability of sampling these points is like, it's quite high, 0.6, whatever. So that's the reason why adding also the higher temperature allows you to cross the barrier. We can also estimate the free energy or whatever observable you want at 300 or 1000 and so on. So the effective sample size I told you about also before, this is the formula, is just where the WK are the weights, so the weight given by the bias or given by the fact that you want to reweight for a different temperature. What's important here is that the effective sample size is typically always bigger than 0 and always smaller than the number of samples that you have in your simulation. And this is what is used to estimate how many steps in temperature you should use. Well, you can run, this is taken from the first 100 steps again. So I'm taking only the initial part of the simulation where the bias is equal to 0. And I can plot the sampling efficiency, so the effective sample size divided by the number of samples. And you can see as a function of the temperature. At 300 Kelvin, it's equal to 1, because here I'm just running unbiased, bias equals to 0 at 300 Kelvin. So the number of samples I get is the effective sample size there. And then you can see it exponentially decays as I try to move to a different temperature. So technically, I can run a simulation at 300 Kelvin and reweight for instance, 600 Kelvin, no? But the sampling efficiency is smaller than 0.1. This means that I have to run a simulation that is more than 10 times longer in order to get the same number of samples, which means the same number of the same level of uncertainty for this simulation. So it's much better to just run another simulation at 600 Kelvin. What we do here with our multi-thermal simulation, so here instead I calculate again the sampling efficiency, the effective sample size, but over the biased simulation. And we can see, compared to the unbiased one, now our sampling efficiency is above 1/3, so roughly 0.4 for this whole range. So this is from 300 to 1000 is what we picked. We could also reweight quite reliably at higher temperatures. So this is just a handy tool that you can use, this effective sample size, to see if you're actually getting what you wanted. So if your simulation is completely stuck for whatever reason, then you would see a very different shape here, no? And then you know that you cannot rely on this sample. And this is instead the histogram of the potential energy. You can see there are 3 peaks, and that would correspond to the 3 temperatures that we are sampling. to give you a better idea, I can simply so I tried to run this instead with just 2 temperatures instead of 3, as I was asking down here in the exercise. And okay, we still see transitions between the 2 states. The shape of the bias has changed. It's more of a 2 composed straight line. These are the delta F's estimates. So the one for 1,000 should be the same, and it's slightly different. And we have more oscillations in general. If we look just quickly, this is our effective sample size. So we have we can see clearly 2 peaks at 300 and 1,000. And it's a very narrow gap here. So we could still reweight for these kind of temperatures. It won't be very effective. So this is not great because, and this is the probability along the potential energy.
Pardon me, I have a naive question.
Yeah, sure.
So you're running with multiple temperatures in your ensemble, and that makes sense to me in terms of combining the energies. Do you have a thermostat? How does that work?
Yes, the thermostat is at 300.
Got it. Okay.
So you choose. I could also choose not to run at 300, but it would make more sense actually to run, I don't know, somewhere in the middle, like at 500 Kelvin. Mm-hmm. And then the equilibration time at the beginning of the simulation would be faster.
Got it.
But I mean, here Alanine is very small. We are just using 3 temperatures, so this is anyway it's very fast. So I didn't bother to do that.
Okay, that makes sense. Thank you.
And what happens in the opposite case, if instead of 2 I choose, for instance, 100, so what happens is this. Just by looking at the sampling along phi, it's much worse. And okay, now we have a lot of delta F, so this doesn't make much sense. But you can see the C of T. Now it makes sense to look at the C of T because it's just one line instead of so many. And it's kind of drifting, no? So this is the profile of the sampling efficiency. So we are not doing great. Basically, if you have 100 delta Fs that you need to estimate, and they overlap a lot because, I mean, the space is very narrow. It will take longer to get a clear estimate. So as a rule of thumb, what I can say is this. It's better to use the minimal number that makes sense of temperatures. So 3 or 4 in this case, it's probably the best choice. No, if you go, so one could think, okay, in replica exchange, I only use 3 or 4 replicas because it's costly, no? So I don't want to run 100 replicas. Otherwise, I need all of that computational power, no? Here, the best choice is maybe to use the highest number of intermediate temperatures. Actually, no, because if I want a uniform sampling along the along the temperature, having 100 intermediate temperature actually gives me a worse shape. And this is the shape along the potential energy. So I think it's reasonable to choose the smallest possible, and this is what the automatic algorithm that chooses the number of intermediate step does. So it tries to go for the smallest number that will cover all the range. Of course, if instead you're not interested into reweighting for all the intermediate temperatures, but only for the first and the last, I mean, there might be different choices for you. But in general, just increasing the number of intermediate steps, it's cheap because you don't need to run extra simulations, but if they overlap so much, you can see here all of them are very close one to another. You are just slowing down yourself. I don't know if it makes sense what I'm saying, but this is just to say you can change this profile, and it's not just the more the better. It's interesting that if you want more sampling, you don't have to increase the number of intermediate temperatures, but just increase the number of multiple walkers, no? And then you can obtain that. So if there are no more questions about this, I'll go to this multi-umbrella simulation. It's just a fancy name to do umbrella sampling with multiple windows, but in a single simulation. In this case, we choose the phi collective variable, and we sample along that. I think the one I gave you, I picked some parameters. I don't even remember. Okay, well, now you do have to choose where to place your umbrellas and what's their shape, and how far one umbrella should be from the other one. This is in unit of sigma. And it's also useful to have a guess of the barrier that you want to overcome. If you do that, you get this kind of behavior. You can see, again, this is the bias as a function of time. At the beginning, the bias it's wrong, but it quickly optimizes. So all the points you see here are still dark blue. And then you basically converge to a fixed bias. This is typical also of OPES. And we can plot, again, the delta Fs, and you can maybe recognize this is the shape of the free energy difference. So in this case, before it was the free energy difference as a function of temperature. Here is the free energy difference as a function of our collective variable, which is basically the free energy surface. And you can, of course, reweight. And here I was just to give an idea, if you do kernel density estimation, your reweight, the shape of the reweight depends on the bandwidth. What happens if you choose different bandwidths? It's interesting here. If you choose as bandwidth for your reweighting the same value of the sigma of the umbrellas, you get the same shape. This is just to say how big the umbrella should be. It's connected to how small the features you care about in your free energy. So usually in umbrella sampling, you have to choose this the kappa parameter, which is the strength of your of the parabola of the umbrella. But I find it more intuitive to instead set again the sigma, which is equal to 1 over the square root of kappa. And the idea is that then you know if you, by running, for instance, an unbiased simulation, you know what are the fluctuations. You have an idea of what the typical, as in metadynamics or in regular OPES, you have an idea of what features of the free energy you care about, and you can easily choose the sigma in this way. So here I asked you to try a bunch of things. I don't know if you did. I can show you some of these results. So if we look at, so here I was setting a different range. So I choose as a maximum value 2. And you can see, so I'm not sampling basically anything above 2, which I think it's fine for me because I wanted only to, I care only about the free energy difference. And I changed also the value of the barrier, and the value of the barrier gives you your initial estimate. So again, I'm not using a bias much higher than the barrier I need to overcome. And these are all the umbrellas I'm placing, much more than before, because I'm using a smaller a smaller bandwidth. And so this resembles more the free energy around the phi. I mean, for instance, I can give you that. Here is if I don't put a barrier. If I don't put a barrier, you see, I try with very high value of the bias, 160. But it's useless in my case. I'm lucky that it doesn't break apart the system. You might have you might try a value of the bias which is very strong and break your system apart. In this case, it just slows down a little bit the initial, but in the end, it converges to basically the same values. Here, I'm overlapping the two estimates, and they basically are the same. So this is the effect of the barrier. What I did here was to instead use the input from, again, an old masterclass where they choose the kappa. I don't know. I'm not an expert of umbrella sampling. I wouldn't be able to decide a kappa value, but it turns out it's 0.07. So it's kind of similar to the sigmas that we were guessing. And the spacing in between the umbrellas, 2.7 sigmas. I was using 2 sigmas. But anyway, we see compared to my initial guess, where I picked a sigma that was too broad, the sampling is more uniform. Now, do we care about having uniform sampling? It depends. If you only care about the free energy difference, then having more uniform sampling, it's not a value in itself. And as I showed before, maybe actually you don't want to waste time sampling this region here, and you prefer to set your maximum of the collective variable to 2, for instance. So you're really free to do what you care about. In this example, I mean, there's not much going on, but maybe you have a complicated system, and if you sample these points, I don't know, your ligand, it's outside of your protein, you cannot get it back into, no? So this gives you very high level of precision of where you want to sample. So if we look at the input, it's more complicated than the one for OPES, where you only basically needed the barrier. But on the upside, gives you much more precision to where you are putting your bias. Again, this was the histogram just to show it's more flat. Now, I'll try to go a little bit faster through the end of the tutorial. You can combine these two things. So again, here we are combining 3 temperatures given by the multi-thermal expansion collective variable and 21 windows. I don't remember exactly. Okay, so again, here it's very simple. You just write down your 2 expansions, the one in temperature and the one with the umbrellas, and you give both of them to OPES. This is a equivalent. This is a fancy way to just write mt dot. So just to give the 2 of them. This is a regular expression to write this, but again, here I'm plotting. It's a little bit longer. We were used to only see the pace here. What I'm telling here, since I'm running more, I'm running here multiple walkers. I want to place the delta F file. I want to place it not inside the folders of the walker, but in this folder. So I add the. Otherwise, it would have been placed in the 0 walker, in the first walker. I'm telling me that I want multiple walkers over MPI, and again, I'm printing down the state. As with OPES method, the state of the file just tells you the current estimate of your. In OPES was the the probability, the reweighted probability, so the compressed kernels. Here it's the free energies, the delta Fs. So it's basically exactly the same information of the delta F file, but in the delta F file, here is time, and for each time I have a long line with all the delta Fs. Instead, the state file as a grid. So you see here we are combining these two. So for the first temperature, 300, I have all the values of the phi collective variable. And then I change to the next temperature, and I have all the values of the phi collective variable repeated again. So, and for each one, I have the estimate of the delta F. Anyway, if I look at this, I have a much better exploration. So here I'm using the same the same input, I think, of the first one. So the idea is that if you combine these two expansions, you have a much better sampling over the collective variable and over the time. Here you can see the bias is now a function of both the potential energy and the phi. And we can again plot the estimate of the free energy along phi. And now it's very useful to look at the C of t, because we have 63 different delta Fs. And this is just one single number that we can look and have an idea of how things are going. Of course, this is just, I mean, you should always calculate the error bars, and that tells you how good you are converging or not. But let's say if this is still in this phase, because you have no idea when you are converged, no? You might stop the simulation here, then you know, I mean, the C of t is completely non-flat, and then you know that you have to run longer. If you see this becoming flat, it just means that the bias is constant, and you still might not have enough sample size to get a good estimate of the free energy. So I would say it's a necessary but not sufficient condition for convergence. And again, you can plot the free energy, for instance, as a function of the temperature. Here I plot it as in units of kBt, so you can see that the higher the temperature, the smaller the barrier along phi, along the collective variable. But if I plot it in kJ mol, they're very similar. What changes is just the free energy difference. Here I can again plot the free energy surface along different temperatures and so on. And here I just show you the distribution of the sample potential energy and of the sample phi. This is not flat, but I have a lot of transitions because again I have a smaller barrier when I increase the temperature. So I said that when you combine it, you get a better efficiency also in sampling the collective variable. We can use, instead of the good free collective variable phi, we can use psi, the other Ramachandra angle. If we run the multi-umbrella alone, this is what we obtain. We have one transition in this given 10 nanoseconds, and our bias is not doing great. We should also plot it as a function of phi. And you see here is the C of t, what I was telling you before. So you look at this and you say, okay, probably we are not converged, no? And this is always here, and it's always one-dimensional, no matter how many variables you are sampling and how many delta Fs you have. Of course, if you are in one dimension, it's good to look at at the plot of the of the collective variable you're sampling, and then you see, okay, I have one transition, probably I'm not converged. But this is nice to have in more complicated scenarios. The estimate, of course, of the free energy is not good, and this is what we're sampling. There is basically still a barrier. Now I do the same here. I was I will update, by the way, the tutorials, so you have all of these solved exercises and you can have a look. This is, everything is the same. I change only this line, and I'm putting the umbrellas over psi instead of over phi. What I obtain is this. So if you remember, let me show you, this is, so this was when sampling multi-thermal plus the good collective variable. And this is multi-thermal plus the bad collective variable. Now, if I only sample the bad collective variable, I have basically zero transition, one transition back and forth, no more, no way to converge. If I only sample multi-thermal, this is always 10 nanoseconds. I have this kind of things. So yes, I have a bunch of transitions, but it's not great, no? If I add to that the bad collective variable, I get a much better result. So the combination is not just, it's not the same as running one and then the other. It improves, it can improve much more. And again, now the C of T looks nice. It is telling me that we are in a quasi-static scenario where we can do reweighting, and we can hope to have enough sample size to get a nice estimate. Here I didn't put the reference, but if you remember, so we are doing a little, we are not good at sampling the barriers, because here we are reweighting with the good collective variable. But the delta F estimate, it's close to the correct one is 9, so we are within the 1 kBT of error bar. Okay, do you have any questions about that? Otherwise, I quickly go to the last bonus exercise. So the final bonus exercise, just to play around, to give you an idea now that you can, what I was saying, I opened my talk by saying that there are a lot of different methods, but if you just look at what they sample, then it becomes easier to group them and to choose what you need to. So here I picked one of these many sampling methods that many people use. It's called Gaussian accelerated molecular dynamics. I don't know if any of you was familiar with this method before. It's pretty straightforward. They add a bias that they call delta V, which is just as you see, an umbrella potential over the energy. So technically, and then they have okay, so this is very straightforward. Then what they do, which is very smart, is that this energy can be the total energy or maybe the torsional energy. So they implemented a way to enhance only a part of the system, for instance, only the torsional energy, the energy of the torsional angles, no? And this is something that really helps. And then they have a complicated way to do reweighting, and a complicated way to choose the parameters. I mean, complicated for me that I'm not familiar with the method, but I mean, it's probably straightforward if you've used it for a while. My point here is, in order to implement this kind of bias potential, you just need, with PLUMED, you just need this lower walls keyword. That it is very flexible. You can choose all of these parameters, but you can set the exponential to 2, which, by the way, I think it's the default, and exactly get this very same expression. That is, it's basically half a parabola, no? So above the center is 0, and below you are pushing. You can also do this with OPES Explorer. Of course, if you only add one of these half parabolas, you don't need OPES Explorer, because you're just changing the bias, and that's it. But on the flip side, maybe I should add a plot of that. You can look how your effective sample size changes once you add once you add this extra bias. What you're doing when you add this bias, it's this. Let's say this is your initial effective sample size. You're pushing it to the right, because you are pushing the energy away from the low energies and towards higher values of the energy. So you're pushing this a little bit. What they try to do is not to push it too much, so that you still have a high enough effective sample size in order to do reweighting at the temperature you care about. So we can do something, we can take this idea and do something slightly different. So I can add a bunch of these. So instead of just moving this, line to the right, I can get something more like this. So I can spread my results over a broad range. So I sample the higher, easy to sample temperatures, and I still have a reasonable reweighting for the low temperatures. I mean, said in other terms, you can do this simply with the multi-umbrella ensemble, and with this keyword lower half only, which gives you these cutted umbrella potentials. And then you can place, instead of just one, you can place how many you want. I don't remember in this example how many I used. A bunch of them. And as you can see, as before, so here I'm using the multi-umbrella, but with the energy as a collective variable. And you can see you do sample well the phi angle. And the distribution of the potential energy, it's much more broader. So this would be something similar to the multi-thermal. It's another way to do a multi-thermal ensemble. This was the shape of the multi-thermal, and this one is our shape. So it's kind of similar. The main difficulty here, at least for me, is that you need to know the value of E, so where to place the umbrellas, and the kappa value. Again, they use kappa. Here I used here I used sigma, and the way you can choose the sigma is, again, what are the fluctuations? What's the shape that I need to get? So I think choosing sigma, it's easier. I picked 12. You can go and use their criteria to choose the kappa, and it turns out like for this example, their criteria was giving like 11. So it was very close to the sigma of the unbiased, which is nice to see. So yeah, this basically, again, gives you a multi-thermal simulation, but it's harder to set it up. I mean, this is my feeling. You need to know what's the minimum energy that you care about and what's the maximum energy you care about, which is non-trivial. I mean, maybe if I mean, I have to run a simulation at 300 and a simulation at 200 in order to have an idea of this. Or they suggest ways to find the average E just with a simulation at your given temperature. So in a sense, you get, from my perspective, at least in these simple examples, in this simple example, you get a very similar result, but you need to know more parameters in order to get it. Of course, things change if instead of using the total energy, you use only the torsional energy as they do in GAMD. But in PLUMED right now, there is not a way to. You only can get the total energy from GROMACS. So there is no simple way to add partial energies. It would be nice to have it in the future, and I'm trying to get it to add this feature. If we can get that, then you can run GAMD or this OPES GAMD, whatever you want to call it, where instead of just one GAMD potential, you combine 2 or 3 GAMD potential. And this gives you a better overlap with so you don't need this cumulant expansion to calculate the reweighting. You can just calculate the reweighting normally because you have a very good overlap, very good effective sample size. Of course, the price you pay for this is that you have in GAMD, you have a fixed bias. And here instead, you would have a bias that changes over time. So you will have to wait an initial transient to equilibrate the bias. But hopefully, as in this case, will be very fast. And what you gain from the reweighting efficiency, it's much more than what you waste in this. But it depends on systems. One has to see, it might be a good trade-off or a bad one, depending on your system. I might add, I'm not going to do it now because I'm sure I will put a lot of bugs in the code, but I will add the effective sample size as a function of temperature for the GAMD example. And it will be different it will not be flat, it will be slightly different. I've actually looked at that, but nothing extremely different. Okay, with this, I'm open to questions now or later, as you prefer. And if you try the method, I'm happy also. You can write an email to me or use the Slack channel or the PLUMED mailing list. I'm available. And I'm always curious to see how people use, because there is a lot of flexibility and different things one can do.
Maybe I'll just shortly comment. Thank you very much for the tutorial. It's very, very, very interesting.
Thanks.
I'm definitely looking to use the OPES MetaD version. That's definitely something that will be introduced into our projects. The expanded one, I'm not entirely sure. I'm definitely looking forward to playing with the Gaussian accelerated MD kind of version because it's something we wanted to look at. But my question was for the expanded one, did somebody look into using it for alchemical transformation simulations as they are commonly used in their discovery studies?
Yeah, so of course it can be used straightforwardly with alchemical. The bottleneck is that, as I said before, right now in PLUMED it's not implemented. The partial you cannot get the partial energies from the MD. So in the paper that the original paper of OPES Expanded, we did a sort of a thermodynamic integration or a chemical transformation from water to Lennard-Jones. And basically we hard-coded so we were calculating again the Lennard-Jones energy, which is very inefficient. So the MD code calculates it, and plus we were calculating it inside PLUMED. It's very inefficient. It worked for the paper to say that it's doable. And but yeah, the main bottleneck right now is the code. But once you have the code and you can get the partial energies from the MD code, then everything is there, and you can do many of the people that do alchemical use replica exchange schemes. You could straightforwardly use the same intermediate states that you have worked so much to optimize, and you can use OPES for that. Another thing, I did an implementation in OpenMM of this OPES expanded, where it's very easy to get the partial energies. But there is an OpenMM plugin for Plumed, but you cannot get the partial energies again. I mean, you can get them, but it needs to recalculate them. So I was able to write it because I need it for some of my research. But it's not an efficient, user-friendly version. It's just a very ugly notebook. But it's definitely doable. I've tried it, but there is this barrier of the code implementation for now. If you know GROMACS or if you know how to get this written, it would be a very nice project. But yeah, right now this is the state of the. And the nice thing, if I can add, is that then it becomes very easy to combine alchemical transformation with collective variable sampling. So oftentimes the problem with alchemical transformation is that you have some orthogonal degree of freedom that is slow. And if you want to sample that with replica exchange, you maybe need 800 replicas because you need 10 replicas in the collective variable plus with this, you can add it for free, basically. So I think there would be also a use case where it makes sense to use this method instead of others.
Yeah, thank you. Very interesting. I'm definitely looking forward to the development in this area. Yes.
Yeah. Thanks. Somebody wrote. Okay. Okay, then I think I'll start by stopping the